Hello and welcome to the feature of the week. In today's video, we will take a look at how and when to use a particular absorption function available in the Monolix library. Absorption through transit compartments. After oral administration, drugs are absorbed into systemic circulation with a certain delay, which is caused by disintegration, dissolution, and release of the drug product, transit to absorption sites, or movement of drug molecules to the absorption surface or through the absorbing site tissue. The standard way of describing this kind of delay is by using a lag time parameter. The lag time shifts the time when the absorption starts, so during times lower than the lag time, absorption is not happening at all. Let's take a look at this Monolix project containing PK data of a theophylline formulation. We can notice the delay by just looking at the observed data, and we can try to model the data with a model that contains a lag time parameter. I will choose a model from the library. We can filter the models by clicking on the lag time in the delay section. I will run auto-init and the estimation of population parameters, conditional distribution, and EBEs. If we take a look at the individual fits plot, it is clear that the absorption phase of the drug is not adequately represented with this model. Early points are underestimated. One of the ways to tackle this problem is to use an absorption model with transit compartments. Transit compartment absorption models describe drug absorption as a multiple-step process. For example, if we assume that the drug is dosed in the depot compartment and then gradually transported into absorption compartment, from which the drug is absorbed in the central compartment, we can add 1, 2, 3, or more compartments to a model between depot and absorption compartments. We used N and KTR parameters so far to characterize the drug transit through the transit compartments, but we can define a new parameter called mean transit time, which represents the average time spent by drug molecules traveling from the first transit compartment to the absorption compartment. We can then use any combination of two of the three mentioned parameters to uniquely describe the absorption. Let's take a look at how the number of transit compartments changes the shape of the PK profile. I've used Monolix to simulate a PK profile using the lag time of 1. If I include a depot compartment in the model without including transit compartments and use the mean transit time of 1, I can see that the absorption phase of the profile changes significantly, and that absorption to the central compartment is first accelerating and then starts decelerating. If we add one transit compartment without changing the mean transit time, the shape shifts a bit towards the shape of the lag time model. And if we continue to increase the number of transit compartments, the shift becomes more and more obvious. Note when that model is parameterized with KTR and MTT, KTR will be the parameter that controls the steepness of the curve. Here we can see the impact of KTR and N change when the model is parameterized with N and KTR. And here we can see the impact of MTT change when MTT is parameterized with N or with KTR. This shows that the predictions depend on the number of transit compartments, and that it is important to optimize this number. However, if we write a model using a system of ordinary differential equations described by this scheme, it can take a while to optimize the number of compartments in a model. For example, we can optimize it by adding compartments one by one, and if the optimal number of compartments is high, this can take a lot of time. The other downside is that models with a fixed number of transit compartments use that number for all individuals. There is no inter-individual variability in the number of transit compartments. It would be great to be able to estimate the optimal number of compartments. Let's see how this can be done. We can write a generalized ODE for the amount of drug in the nth transit compartment in a system with n transit compartments. Analytical solution is given by the function shown here. This means that the amount of drug in the absorption compartment is represented by this. Because of the use of the factorial function, n can only be expressed as an integer, which would make it impossible to be estimated by SAEM like the other parameters of the model. However, we can use the gamma function for calculation of factorials, and since this function is continuous, non-integer numbers can be used to estimate the number of transit compartments. You can use already mentioned equations to write models with transit compartments directly in the MLX but certain MLX macros, such as PK model and absorption, can be used with keywords KTR and MTT to indicate that the absorption is happening through transit compartments. Note, however, that analytical solutions for the models with transit compartments are not available, which means that the models containing transit compartments will take a longer time to run than the models with simple first or zero order absorption. Models with transit compartments are included in the Monolix library as well. So let's try to use a model with transit compartments to model the dataset we previously tried to model with lag time. Instead of lag time, I choose transit compartments in the delay section of the library, auto-init the initial estimates, and run the model. We can clearly see that the earliest points are not overestimated as before, but I overlaid the fits from this and the earlier project using lists of connectors, so we can compare the individual fits directly. In summary, when it is apparent from the observed data that the acceleration of absorption is happening, lag time models may not represent the absorption process well. One of the possible solutions is to use models that have transit compartments. Number of transit compartments can be fixed or estimated, integer or non-integer values can be used, and models with transit compartments can be chosen from the Monolix library or written in MLXtron using macros or differential equations. Thank you for listening and have a nice week.